In this video, we would like to talk about the energies of a particle in simple harmonic motion. We'll start with a potential energy. That's the energy possessed due to its position in simple harmonic motion. We know whenever a particle is in simple harmonic motion, to produce a displacement, we shall do some work. After doing that work is stored in the format of a potential energy. So if I find work, I have already found potential energy. So let us consider that. When force F is applied for a particle in simple harmonic motion, produce small displacement dy. We must have done some work. As the displacement is small, work done is also small, so I'm calling it like dw. Work done is how much? Force into displacement. Of course, it is done against the force, but we are not putting a negative sign because here we are intended to find only a magnitude. But what is the value of that work? The force, that is mass into acceleration. We know for a particle in acceleration, for a particle in simple harmonic motion, acceleration is omega square by dy. The small work done to produce a displacement dy is this much. But we need to do so many of these displacements together so that we'll be doing a total work done. So to get total work done, we shall integrate the above equation, this equation. So integral of dw equal to integral of m omega square y dy. Integral of differentiation of work done is equal to work done. M omega square is constant that can be written outside the integration. Integral of y dy. So the work done is equal to M omega square. There is a formula in integration. Integral of x power n dx is equal to x power n plus 1 by n plus 1. So integral of y power 1 dy, that is y power 1 plus 1 by 1 plus 1 as per this formula. So work done is equal to m omega square y square by 2, or in the simple sense, half m omega square y square. That's the total work done. That work done is stored in the format of a potential energy. So potential energy is half m omega square y square. May sometimes people call this as I told you earlier, like a spring constant. Okay, so half k y square also can be written. We'll talk about it later when we are talking about springs in particular. So it's very clear potential energy is a dependent of displacement because half m omega squares are constant. So what we can say, mean position displacement is zero. Y value becomes zero. So potential energy becomes zero. At extreme position displacement is amplitude. So potential energy is half m omega square a square, that is maximum. So if you draw a graph, if you draw a line at mean position and extreme position or at interim position. At mean position, potential energy is zero. At extreme position, potential energy is maximum. At interim position also, potential energy is maximum. That's all about potential energy. Let's try to find out about kinetic energy. This is body in simple harmonic motion. Kinetic energy of any body is generally represented as half m v square, where v is the velocity of the particle. In simple harmonic motion, we have derived that equation as omega into root of a square minus y square. Substituting this value in the above equation, kinetic energy becomes half m. In place of v, this value, omega into root of a square minus y square, v square whole square. Then this value becomes half m omega square of this root and square will go a square minus y square. That's the equation for kinetic energy. So if you notice little carefully, this is the equation for kinetic energy. This is the equation for energy. So how does it varies if you look little carefully? It depends on a square minus y square. So if you say at main position displacement is zero, so kinetic energy becomes half m omega square a square minus zero square. That is half m omega square a square. That is maximum. Whereas at extreme or interim positions, displacement is amplitude y equal to a. Put there, kinetic energy becomes half m omega square a square minus a square, that is equal to 0. So what is being noticed here is main position potential energy is 0, but at main position kinetic energy is maximum. Extreme position potential energy is maximum, but extreme interim position kinetic energy is 0. So you can see one energy becomes more, another energy becomes less. Right? At interim position, potential energy is maximum. In interim position, kinetic energy is 0. So one energy increases, another energy decreases mathematically. And let's talk about the total energy, which is very simple now. We know total energy of a body in mechanical motion is sum of potential energy and kinetic energy. We have derived an equation for potential energy as half m omega square y square. Kinetic energy as half m omega square a square minus y square. In both of them, half m omega square is common. So here y square is remaining. Here a square minus y square is remaining. Y squares can be cancelled. This is half m omega square of a square. That's the maximum energy at any state is the total energy itself. So this clearly tells you that energy is conserved at any point. One energy increases, another energy decreases, but the total energy always remains constant. It's an explanation of conservation of energy for a body in simple harmonic motion. Notice that one energy, another energy, summation of these two energies. So if at any point, if potential energy is increasing, kinetic energy will be decreasing. The total energy remains constant. Or if potential energy is decreasing, kinetic energy will be increasing. And the total energy, half m omega square a square, always remains constant for a particle in simple harmonic motion. That's how we can derive expressions for uh, potential energy, kinetic energy, and total energy of a particle in simple harmonic motion. That's it.